Hi everyone. So we are online again, and this is Saturday. So we are excited to be with you. I know we took a short break the past 2 weeks, and we had a different presentation going on a different channel, but we're going to upload that for you as well. So here we are again with the AI deep learning enthusiasts, and we're going through the online discussion of the deep learning book, Saturdays at 11 a.m. So what we're doing here, we have participants actually volunteer to go through each chapter of the book. They read it ahead of time, they put together a short presentation, and then of course we get online and have a discussion, and of course answer any questions that you might have as well. So the goal, of course, is to make sure that everyone gets the most out of this experience, including reading the material, adding to the discussion, doing presentations, and learning together as a community. If you'd like to sign up to be a presenter and to volunteer to read the material ahead of time, you can find our present up sign up form either on our meetup group or on our YouTube live session in the details in the comments below. And then what you do is just you register your name for each chapter at a time and kind of go from there. If you want to join us in person as well, we have in-person sessions in San Francisco, and there we're going through the same thing, the deep learning book. We also have other sessions and workshops that we host for people on AI and deep learning. So without further ado, we would like to introduce our volunteer presenter today. This is Sohaib. Sohaib, do you want to say hi to everyone?
Sure. Hi, everyone. This is Sohaib. I am currently working as a data scientist at a startup in San Francisco. Before this, I was in grad school studying theoretical physics, decided to make the switch over into data science and machine learning. And so deep learning is, it's something we all get to hear about quite a lot. And it's gotten me excited, especially because I think there's enough math to keep a physicist interested, but also, there's so many applications that we see, using these set of techniques every day that, I guess it's fair to say that everyone who's made it to this meetup is also naturally very curious and, interested in learning this subject. So I should say, just as a disclaimer that I don't know this stuff as, I know this stuff just about as good as any of you. This is stuff that I'm learning for the first time. So if any of you feel you have something to add to the conversation, feel free to add and interject at any point. I'd love to hear what you guys have to say as well.
So that is a little reminder. Do please post in our chat thread and ask any questions that you might have in the chat, and then we will go ahead and read those aloud for the presentation, so you guys can add to the discussion at any time.
Cool. And Laura, just a quick question. I just did a full screen. Can you guys see the full screen of the slides?
Yep, we're on it.
Great.
Yep.
Okay, so today I'll be talking about the second half of the chapter on sequence modeling, specifically recurrent and recursive nets. I believe Pankaj talked about part one, and I'm not exactly sure whether he included or excluded bidirectional RNNs the previous time, but I'll just cover these quickly and then move on to the next section. So just to briefly recap, recurrent neural nets were essentially neural nets of the form. They were essentially, they had some kind of a recurrence relationship between a given between the state of the network at some given time step t, and at a future time step t+1. So essentially what we're saying is we're conveying whatever the information was contained in the state of the neural network at some particular time, and we recur it forward in time. What bidirectional recurrent neural nets do essentially is they propagate that information not just forward in time, but also backward in time. So the motivation primarily is, when your input sequences, remember that the time index t is, we give it the name time index just to, I guess, help us visualize and make it intuitively clear that it's some sort of an ordered sequence. But really, it could just be any ordered sequence, right? It could just be words in a sentence or anything where the sequence of the inputs matter. And in particular, where in sequences where the context matters, for example, speech or handwriting, where, for example, if if I say a word, it matters, the words that are going to follow the word that I just spoke are going to matter and are going to serve as a context to what I just meant by that, by the word that I just said, right? Same as with handwriting. So there are several examples of sequences where the context matters, and in such instances, we ideally should have knowledge about the future as well as the past. And so in this current architecture that's displayed in this figure, h of t, as usual, just denotes the state of the sub-RNN that's moving forward in time. This is the same usual case that we saw in the first half of this chapter, where we're propagating, like some information from input to the hidden layers, to the outputs, and then calculating the losses given the actual predicted outputs. Sorry, given the actual labeled outputs. And we propagate, we recur the information forward in time, where time is moving from left to right. But in this case, we also have an additional sub-RNN that moves backward in time. So this is, how we can propagate information from the future of some sequence to the present. And in this way, we could extend the architecture to go forward or backward in multiple dimensions. And in, if we have n dimensions, then we would have 2n, 2 times that number of sub-RNNs. And in particular, if we're looking at, if our input data is 2D images, then essentially what we're saying is, like, if we're looking at any one image, then we could capture long-range lateral interactions between features. So example, like a 2D, imagine like a 2D grid. And by lateral interactions, we just mean like, like something that can be forward or backward in the direction that you're looking at. So these can be great to train, like to basically have information across the entire image talk to each other. But they, in practice, they can be more expensive to train than convolutional neural nets, which are still, I suppose, better in image processing. So the next architecture that we would discuss is the encoder, decoder, or sequence-to-sequence architectures. So the basic premise here is that, previously we've seen architectures where we map a constant size vector to some sequence, or we could, like have basically the same length sequence mapped to the same length sequence. In other words, the sequence, the length of the input sequence X has to match the length of the output sequence Y. But over here, we can allow for input and output sequences of different lengths. And the applications would include such things as speech recognition, machine translation, or question answering, where, for example, the length of the sentences that you input and the length of the sentences that you want to output could in principle be different. And the way we do this is by, it's essentially composed of 2 sub-RNNs again. The first RNN, the input RNN, is called the encoder. And what it does is essentially it takes the input sequence X and outputs a vector or a sequence of vectors that we call here C. And C is really shorthand for context. So the C essentially encapsulates all or encodes all the information provided in the input sequence. And then the C is then what's further fed into the decoder or the output RNN. And the architecture is, as seen here, the encoder provides the output to C. C then feeds into the decoder RNN over here. And both these RNNs are trained jointly in order to maximize the average of the log of the conditional probability, the output sequence given the input sequence. And so now we can also talk about deep recurrent networks. Typically, from what we've seen with RNNs before, RNNs can be decomposed into 3 essential blocks. There's an input to hidden layer. There's a hidden to hidden, right, which is basically given by this recurrent relationship. And then finally, there's a hidden to output relationship. What the basic idea with deep recurrent networks is to introduce depth in each of the above blocks. And so the simplest example is over here, where we've just introduced an additional layer of block over here. And the idea over here is that the lower levels, the X's and the H's, those transform, well, I guess the H's over here, these transform the raw input to some more appropriate transformations. And so, like, it's just, if you think back to the example of how adding a layer helps a network learn the XOR function, remember that we couldn't learn the XOR function with just a linear map, but by just adding another layer, the first layer was able to transform the XOR input into a more suitable input, which a linear function can then learn. So something similar is basically happening here, where we take the raw input, convert it to a more appropriate input, and then that's what's later fed into the higher level layers, essentially. We could also do the following, where we add extra layers in the recurrence relationship. So remember, this black box over here is used to denote recurrence between the current time step and the next time step. So it's just it's a length 1 recurrence relationship. But what we can do also instead is like just add an intermediate set of layers between h and its next time step, essentially. And then finally, we could also mitigate longer distance from t to t plus 1 by adding skip connections. And so basically, like, I mean, what this architecture in the middle, one of the problems that it introduces is that these relationships can be very hard. They can start becoming expensive to train. And so in order to mitigate that, we can essentially just introduce these sort of skip connections, which skips this extra layer part and just does it in the usual way. So that's that makes it somewhat simpler to train than the architecture in the middle. Recursive neural nets are essentially a generalization of the computational graph. So previously, what we've seen in recurrent neural nets are essentially chains, right? So when we looked at the computational graphs, they're almost like, if we unfold, for example, this first graph in figure A, it would basically look like repetition of these same 4 layers across time, right? So that's essentially a chain structure. And instead of a chain structure, what we could also introduce is something like a tree structure. So what happens here is that for a sequence of length n, the main advantage is that for a sequence of length t, the depth, and what I mean by the depth is strictly the number of compositions of nonlinear operations. The nonlinear operations, of course, being our activation functions and so forth. Those can be reduced from order t to order log of t. So in a chain-like structure, where we're going from like left to right, essentially, like, the operations involved are order t, where t is like the length of the entire input sequence. But if we adopt a structure like this, where say, like, we're looking at an input sequence of length t, then this tree structure allows the number of those operations to reduce to order log of t. And the simplest way to look at it is if you assume a tree with the branching factor of 2, then we can see that, like, if the depth of the tree is just like depth over here, then if you just solve for 2 raised to the power depth, and if that's equal to t, then you can see that, like, the depth becomes log of t. One of the open questions we have is to how to best structure the tree, and in practice, it really depends on the problem at hand. Ideally, the learner itself infers and implements the appropriate structure given the input. But I believe there are a bunch of references noted in the book. I didn't reproduce them here, but I believe that this is an open research problem as of the writing of the book. So what we just discussed, in the previous slides, I guess, is ways to basically have long-range dependencies or long-term dependencies. In the case of images, we could have long-range dependencies. Like, for example, pixels on the very left-hand side talking to pixels on the very right-hand side. And in the case of time-ordered sequences, we're talking about long-term dependencies, where, for example, if you have something happening now, if it depends on something that happened way back in the past, then you would ideally want that dependency to reflect itself in the present. But there is a problem in introducing such long-term dependencies, and the basic problem is that gradients, when propagated over several time steps, tend to either vanish or explode. So we can think of, and I think we saw part of this in chapter 8 as well. But just to sort of recap in the current context, we can think of the recurrence relationship this relationship where H, the state of the current hidden layer, is dependent, via this weight matrix on the state of the layer at the previous time step. We can think of it as essentially a simple recurrent neural net that lacks inputs and any nonlinear activation functions. And in particular, we could apply this relationship recursively, t times, to obtain this simpler form as a function of just the 0th time step state of the hidden layer. And in particular, if W admits an eigendecomposition of this form, where Q is some orthogonal matrix, then we can further simplify this as follows. So we're just replacing W over here with this expression. And what this tells us essentially is that if lambda has eigenvalues that with magnitude less than 1, then because we're raising it to the power of t, if we have many time steps, then those eigenvalues will tend to decay away. And if those eigenvalues have magnitude greater than 1, then they will tend to explode. And eventually what this causes is that any component of H0 that is not aligned with the largest eigenvector, it just tends to be discarded. So this is a problem that's, it's inherent to recurrent neural nets in particular. So for non-recurrent networks, we can always avoid this problem by choosing different weights at different time steps. So notice that, and one way to see this is to, if you imagine just a scalar weight, so instead of this whole W matrix, just imagine a simple scalar weight W that gets multiplied by itself several times at each time step. The product W raised to the power t will either vanish or explode given the magnitude of W, similar to what we argued over here in the previous slide for the eigenvalue magnitudes. But on the other hand, if every W at every time step is independent but identically distributed with mean 0 and variance v, then the state at the time t is the product of all the WTs. And the variance of the product in particular is order v to the n. So what that means is that for non-recurrent deep feed-forward networks, we can always just set the desired variance v star by sampling the individual weights with variance square root of n of that v star. Because once you multiply all the variances, it'll just come out to be whatever your desired variance is. The important thing is that all of those weights at every time steps are independent. They can be identically distributed, but because of this independence now, we can essentially achieve this desired variance. But this is, again, for non-recurrent deep feed-forward networks. An open problem for RNNs is to solve this challenge of long-term dependencies without the problem of vanishing or exploding parameters. And so I'll talk about a few strategies of how this is currently achieved, or various approaches that are being tried out and researched to evade the problem of vanishing or exploding gradients. And the first of these is something called echo state networks. And the idea basically is that the hidden to hidden in a recurrent neural net, the hidden to hidden and the input to hidden weights are usually the most difficult parameters to learn. And what echo state networks do essentially is they set the recurrent weights such that the hidden units capture the history of past inputs and learn only the output weights. And in liquid state machines, it's the same as above, except that they use binary output neurons instead of continuous valued hidden units. And this approach is collectively referred to as reservoir computing. The name is kind of inspired from the fact that these hidden units form a reservoir of temporal features, capturing different aspects of the input history. So, in order to tell, how specifically the ESNs actually achieve their strategy, I'll have to step back and talk a little bit about spectral radius and why it's important to, keep it bounded. So remember that the spectral radius essentially refers to the largest eigenvalue of the Jacobian at some given time step, where the Jacobian, remember, is given as the partial derivative of the current state with respect to the previous state at the previous time step. Now further suppose that this Jacobian has some eigenvector v with some eigenvalue lambda. And by the way, I should apologize. I wasn't able to write the Greek letter lambda, so I just spelt it out. Same with the with the symbol delta. I just like spelled out in words that symbol, but if you want to refer back to the book, it's just the Greek letter lambda over there. And briefly, what this says is that you have this Jacobian matrix that has some eigenvector v with some eigenvalue lambda, and let's say that we want to do backpropagation, and we start with some gradient vector g, and we want to backpropagate that through time to calculate the gradients with respect to the various parameters in our network, and compare that backpropagation to if we had started instead of g at the vector g plus delta v. And remember that this difference could be very small. Like, we can always control for delta being very, very small. But the main point is that since v is an eigenvector of j, the two different executions after n backpropagation steps will diverge by delta lambda raised to the power n. And just as we argued before, if the magnitude of lambda is greater than 1, then this can grow exponentially large. And if it's less than 1, it can vanish. So the strategy in echo state networks is to fix the weights to have some sort of bounded spectral radius, such that the information is carried through time but does not explode or vanish.
Hey, Soheeb, we have a quick question in the chat.
Yep.
So the question is, Abdullah was wondering if the gradient exploded or vanished during training. How do we know?
I think that's a great question, and I think if the gradient just vanishes, then one way you could figure out if that's happening is if like you're just moving along a constant. If the value of that parameter is just saturated. Because if we're doing gradient descent, then at every time step, we're changing the values of like say you're modifying the cost function, right? So the cost function changes from j to j minus some value times del j, right? Or gradient of j. So the gradient of j is flat along some direction, which means it's become 0. Then you're not moving along that direction anywhere. Then you're just like you've reached a flat plateau along that direction. So in principle, I guess that's one way you could do it, is to just look at how the cost is changing, with respect to different parameters. Of course, that could mean that you've hit some sort of a saddle point as well. I'm not exactly sure, but perhaps that's one way of figuring that out.
Wonderful, thank you. And we also had another participant add a comment as well. It's Sharif. He said, as we backpropagate, the gradients calculated over some parameters will just be close to 0 or very large. So that's just another way to think about it.
Right. That's true. Yep. Okay, cool. Thanks for that comment. So the strategies, various strategies that for handling multiple timescales. So what we want to do is we want to design models that can operate at multiple timescales. For example, we could have some parts of the model operating at fine-grained timescales, and we could have others at more coarse-grained timescales. And the idea being that the former would basically have would capture more shorter term time dependencies, and the others, the more coarse grained scales, would have more longer term time dependencies modeling. And one way to do that is to add skip connections through time. So what that means is adding direct connections from variables in the distant past to variables in the present, instead of just from time t to time t plus 1. Leaky units and a spectrum of different timescales. What this means is that we can design units with linear self-connections and weights near 1. So as an analogy, we could consider accumulating the running average mu of t. And again, over here, that Greek symbol mu, I just borrowed this equation from the book, but I'm just calling it mu over here. The running average of this thing, so mu of t is the average of v of t, some variable v. If we have this, if this gets updated via the following equation, then we can see that like if alpha is set very close to 1, then essentially this term drops out, and the running average remembers the past for a very long time, which basically just means that like, the dependence of mu of t minus k for very large k, it's very strongly related to each other. But on the other hand, if alpha is very close to 0, then it doesn't have a very long memory of the past, essentially. So you could think of like you could replace mu with hidden units, and this alpha, what this does is like it basically creates a self connection from the hidden unit at some previous time step t minus 1 to the current time step t. And if the weights are very close to 1, then it can essentially behave similarly. And you can have the past talking to the present over a long time scale. Another approach is to simply remove length 1 connections and replace them with with a length of a larger number of connections. So instead of like t minus 1 talking to t, you could have like t minus k talking to t, essentially. Okay, so as of the time when the book was written, which is what I mean by as of now, the most effective sequence models, presumably, that are used in practical applications are gated recurrent neural networks. And these include both the long short-term memory, or the LSTM networks, and networks based on the gated recurrent unit. The basic idea of both these structures are to create paths through time with derivatives that don't explode or vanish by allowing connection weights to become functions of time. Leaky units can allow network to accumulate information over a long period of time, as we saw like before in this case. Like, so this is an example of a leaky unit, right? It can have information from the distant past accumulate for quite a long time. But there should also be a forgetting mechanism when that info becomes irrelevant. So, for example, if we're parsing through sentences in a text, or if we're just like parsing texts, we might want to forget the information that we received in the previous sentence, or the previous paragraph, or the previous chapter, or something, right? Like we could, we might want to keep that information we might want to store it temporarily for some time. But we want to eventually forget it. And that's basically what gated RNNs, I think, accomplish. So the first example is the long short-term memory, or the LSTM, where the state unit SIT. So in the figure over here, I've drawn the LSTM cell. There's a couple of details over here that might not become relevant until a few slides. But essentially, what this structure involves is a state unit that has a linear self-loop, similar to the leaky units described in the previous section. So in other words, it has it has some recurrence relationship with itself. The self-loop weight is controlled by a forget unit. So we introduced this forget unit, which essentially it takes in some biases, it takes in the inputs, and it takes in the state of the hidden layers at some previous time step. And of course, there are weight matrices for each of those to respectively. And of course, there's the bias. And then finally, there's an activation function, which in this case is assumed to be the sigmoid function. So this forget gate is used to update. It's used in the recurrence relationship of the state cell itself. So this SI talks to the previous time step, but mitigated via this forget gate function. So this forget gate controls, this is sort of like alpha, in this equation. So this basically tells us, like, how much the current state depends on the previous state directly, right? And then there's an external input gate as well, which essentially, it's very similar to the forget gate. Like we can see from its structure that it's like essentially the same thing as the forget gate, but it has its own, it has its own set of parameters. The biases, the input weights and the recurrent weights. Those are all different for this particular gate, and it's again activated by some. Well, it's multiplied. Sorry, it's multiplied by its own sigmoid function. And so these together, give us the state of the LSTM cell at any given point in time. The output of the LSTM cell can also be shut off via the output gate. So that's essentially, it's a similar structure again, but again, this output gate is, it just gives it has its own set of biases and weights for the inputs as well as the previous hidden layer. And so in particular, basically, we could also, one thing we could also do in addition is we can choose to use the cell states SIFT as an extra input with its own weight into the 3 gates of the ith unit. So that's what this part over here does for you. So if this is the given state, then we can feed that back in, similar to what we're essentially doing, in any of these time steps, in any of these, equations. We can feed it to the current input over here, and that's an extra thing that we can do. But essentially, the punchline is, and I think there's like more variations on top of the ones that I just wrote out over here. But like basically, the basic idea is always that we have some sort of a recurrence relationship, but that recurrence relationship involves some forgetting over here. There's this usual kind of like, dependency via some activation function on the inputs and the previous layer. But in addition to all of that, we also have a way to forget the previous states. And the parameters of that forgetting action, those can be learned. Those are like, that forgetting action is basically controlled by these parameters, the biases and the weights. And these can be learned if we, for example, have some sort of like, like supervised learning setting or something. So that's LSTMs. Other gated RNNs that we can consider are as follows. So the main difference in the one that is presented over here is it's essentially a single gating unit that simultaneously controls the forgetting factor and the decision to update the unit. So essentially that just means like, there's an update gate. And then finally there is and I might have, I think there might be, oh, no. Okay, never mind, sorry. So there's an update gate over here, which controls, which is, it controls how much the current state of the network is proportional to the previous time step of the network. And then 1 minus that, I somewhat think of this as like something akin to a probability, although it isn't exactly, but maybe you could interpret it in that way. I'm not exactly sure. I'd be curious to hear if someone knows about that. But essentially, like, this is a sigmoid activation function. The update, this term essentially controls this, how much the current state of the hidden layer depends on the previous time step. And then finally, 1 minus that factor will control via a sigmoid activation function, the reset gate. So the reset gate basically just like, it talks to actually the current time step of the hidden layer. So this is kind of like, it's I guess you could call it a recurrence, but it's really, when I think of recurrence, I think of like, some state depending on the previous time state. But this is really like, this is introducing factors that depend on the current time step. So this is like, this is still t minus 1, so never mind. Okay, so this is basically just, I think like, well, I'd be curious to hear if anyone has a better intuition about this, but essentially, I think what my kind of like, loose intuition about this was just that there's like some, with some probability, we updated with respect to the previous hidden state, and with 1 minus that probability, we updated with respect to, whatever this particular state gives us, which is another thing, it's a different combination of the previous state as well as the previous inputs and biases. But apart from that, I don't really have a better intuition for what this structure really means. But I guess part of the main point is that both gates can individually ignore parts of the state vector. So I guess that's the main forgetting mechanism in these guys. And that was about it. I didn't have time, unfortunately, to cover the remaining sections, which were about optimizing the gradient calculations, I believe, in the neural networks and the recurrent neural networks. So if anyone else has anything to add at this point, or any questions, we could go into that.
Yeah, that's not a problem. So just a reminder for anyone who does a presentation, you're not expected to, go on for a full hour or any specific amount of time. Really, it's just we want to make sure that you cover as much as you can to kind of help people go through this chapter as well and just supplement their learning experience. So we do have a few more comments in the chat that we can read aloud as well. So Sharif says, one way to think about it is that the network can learn the values of UI to turn on or off past by choosing values closer to 0 or 1.
Okay. Is that the case of gated arguments?
I'm pretty sure that's what he was referring to. And just so you know, so there's usually about like almost a minute delay between us talking and them actually seeing us. So
I see.
we can give them like a minute to catch up as well.
Okay.
And there was a few other comments in here also in reference going back to that exploded or vanished question that was brought up previously. So specifically, Abdullah wanted to know, he was trying to train a network in TensorFlow and wanted to ensure that there were no problems. And Sharif suggested that he could get the gradient values with TensorFlow by using tf.gradients.
Okay.
And then also, there are ways to optimize the model using optimizer.compute_gradients.
Okay.
And he said these will need to deal with the exploding gradients, such as doing gradient clipping, and that TensorFlow helps you do that already. And he also sent a link here for reference through the GitHub, but what I can do is also post that link in our spreadsheet, because in our spreadsheet there's a section for additional resources, potentially that people can view if there's something interesting that people refer to. Yep, so okay, you got the chat up. So yeah, so if we can give people a minute to see if there are any other questions or comments that are related to this chapter. We'll see. Okay, so Sharif has said yes for both LSTMs and GRUs for those parameters that use sigmoids since they are gated between 0 and 1. Yeah, so so that's great. Let's see. So we do have another 20 minutes left. Was there any other area of this chapter or any specific concept in this chapter that you think is the most important for people to actually gain understanding of going forward? Like what aspect was, do you think was most valuable? So
sorry.
Yeah, that's okay.
Sorry, I was just reading through the comments. Could you, did you want me to say if there were any other interesting parts?
Yeah. So like what aspect was most valuable to you? What do you think is the best takeaway for participants from this chapter?
I mean, personally, I found the various architectures, interesting because, I mean, like online, at least in my personal experience, like I've just kind of seen, several very good introductions to RNNs and LSTMs, but I think like just, sort of like the different architectures and the figures accompanied by the equations, I think like that was very helpful for me to kind of like, gain an intuition for why, one thing is important versus the other. But I can't really say like, I mean, how any particular section would be more useful to the other, because I guess they're all sort of interrelated. But I like the overall kind of, structure and organization of this chapter in the sense that it was, it was very like well divided into like, I mean, here's an architecture that does this. Here's the advantages. Here's the disadvantages. Here's like, I mean, not in all cases. I guess what I would have loved to see is like the computational graphs as well as the accompanying equations for each and every one, just to be thorough. But I guess, once you see a couple of examples, you could, in principle, just work out the equations by yourself. I'm all about the equations, but yeah, I mean, I guess that's the main thing I kind of liked about this one is that it was, it did have some like, quite a lot of substance in that regard. Like, I mean, there were definitely sections in here, uh, which like in other chapters, it's been, like that were kind of difficult to read through, just because there were mostly words and, very little kind of like technical details. But I think, with especially the sections that had, explicit graphs and equations and everything, it was kind of easier for me to follow what was going on. So I thought that was cool.
Definitely. So with the LSTMs, if you go back to that architecture, do you think it's very similar to neurobiology specifically? Do you think that's what they model it after?
Oh, I would love to know that myself. I
Yeah.
don't know much biology at all, but that's I mean, yeah, I mean, I would. That's a great question, and I mean, I don't know the answer to that, but I would love to know the answer to that as myself. I mean, I know, like, I mean, I guess, like, the authors of the book did mention that, I guess, the original motivation was, um, yeah, of neural networks in general was biological, but after some time, like, I mean, especially like now, they're not, like the motivation to, produce more research isn't necessarily biologically inspired. It's just, whatever helps you do the job, I guess. But
Yeah, definitely.
yeah.
And so, okay, so we have a few links that were posted by Abdullah and Sharif as well, specifically on
Awesome.
LSTMs.
Okay.
Here, I will put these in the chat for you. Do you want to,
Awesome.
or actually you can click them too, either if you want to, and pull those up also for our viewers. We can see
Okay.
what those were. So it looks like we have Exploring LSTMs. He's a really great example
Oh
that,
yeah. I think I read this one. This was really good. I think the thing that spooked me out about this particular, so I guess, like, I mean, just as a recap, this is something I saw from, like, the Kaggle.com posted on Facebook, I think.
uh-huh.
But this is, like, I mean, I think he does a good job of, like, just walking us through, like, I mean, what a neural net is, and, like, I mean, why RNNs are important, etc. Um, but I think what the thing about this blog, what freaked me out the most was, like, there's this part over here where, the author essentially, I think, just like trained it on some, like, code repository or some code base, and this is an example of a code that the LSTM generated, I believe. Um,
Interesting.
and if you look at it, I mean, this is like pretty well written code. I mean, it even has, like, unit tests over here.
Yeah.
And that's like, I love this line. I mean, I'm a data scientist myself. Like, I mean, so it's like, while the code certainly isn't perfect, it's better than a lot of data scientists I know.
That's great.
Like, well, robots are coming for our jobs now too. Great.
Yes, yeah, definitely. Actually, they've said that AI is being developed that
Yeah.
can create its own AI fairly easily.
Right.
Yeah.
Yeah,
Um,
that was pretty
so
crazy.
yeah, definitely. So we do have another question.
Mhm.
So Bill Ross has said, won't, for example, TensorFlow display status such that you can tell the percent of gradient explosion / vanishing?
Honestly, I haven't used that much TensorFlow to really say,
Mhm.
but I think, I mean, like, it sounds from one of the examples that either Sharif or Abdullah, uh, I think Sharif might have said something. Let's see, wasn't, yeah, there we go. Like, maybe, I don't know. Maybe one of these guys can, like, answer this question better for us. But I mean, I would totally believe it if someone told me that TensorFlow already has a way to give you that information, because it sounds like it's something pretty important to know.
Right.
And but I'm probably the wrong person to ask that question.
Definitely. And then it looks like Sharif also noted you can also use TensorBoard for visualizing parameter values that helps
Right.
determine whether the network is learning anything. So this is an interesting point, actually, that you've brought up. So you're a practicing data scientist, and you very much value the mathematics behind AI and deep learning. But there are other people who think when they think of data science or artificial intelligence or machine learning, they think more about the engineering aspect and using APIs and software like TensorFlow and Python and scikit-learn. And so I'm interested, based on your experience, what's really the difference in the industry? Because you are a data scientist by trade, but yet you don't actually do a lot of the engineering.
Well, that's only partially true, really, because of course, as data scientists, as a data scientist myself, like I'm essentially just coding every day. But I think for me, like right now, the products that I'm working on don't necessarily use deep learning, and we don't have to. For me, this is more kind of like like an R&D project, and from what I tried, like like with just simple implementations of TensorFlow, of like trying to implement some kind of like a deep learning project. I quickly found that there's lots of really good tutorials I can use to sort of like just put in some kind of a prototype and start playing around with it. But without learning the theory, I wasn't exactly sure what to do with it.
Okay.
And that's what really got me interested in like learning, like going through this book, understanding what it's what the theory is all about. Like like if I'm implementing like an RNN LSTM, I mean now. I guess I could go back to TensorFlow and try some of these things and hopefully use some of the pointers that Sharif and others have given here, and that would be helpful. But like now I know, like, okay, so there's like these different architectures that you can implement, presumably in TensorFlow, and here's what they mean under the hood. Because I personally felt, and I mean others might have had like a different experience from mine, but I personally felt like you needed to know at least the minimal, you need to have like a minimal knowledge of deep learning before you could even use TensorFlow, which is kind of different from using something like scikit-learn. Like like if suppose like I have zero knowledge of how a naive Bayes classifier works, I could always, all I would have to know about it is that like it's just like some kind of like a classification algorithm, and I could just like use it, treat it as a black box from scikit-learn and just implement it, right?
Right.
Of course, it always helps if you know what's actually happening under the hood. But with something like TensorFlow and deep learning, I felt like I needed to know a bit more before I could really get comfortable with implementing any solution. Because I felt like a lot of the details was just in the architecture.
Yes.
And without knowing which architecture is useful for what, like I felt like I just would have been lost. So, but to sort of go back to your question, I think like it's an interesting question of like one of like engineering versus the data science aspects. I guess in my current role, it's really very fluid, because I mean we're a startup and we're a very small team, so like I actually get to write production level code every day, and like that's kind of like still my main focus. But as kind of like the data science, the data scientist on the team, like I have to sort of like think about how to move in like different directions, especially when it comes to like incorporating state-of-the-art analytics tools such as deep learning. But like I can't justify that as an engineering solution if I don't even know what's going on, right? So for me, like, I mean, right now the sort of order of things is like, I mean, learn the basic theory behind it, and then like start move on to the implementation.
Definitely. That's a great response, actually. And I think it'll probably resonate with a lot of our viewers or people that are interested in getting into the field and they're not really sure where or how to start, or how the job would actually be once you're in the industry.
Right.
And I'm sure it evolves, right, over time, especially as these new
Absolutely.
technologies are created and explored. But I guess going back to that point a little bit then, on the topic of recurrent and recursive nets, can you think of like a real world example where someone would want to utilize this type of architecture?
I know I do. I mean, I work with time series data every day. And so like, with time series data, like, of course, that's like a very natural sequence, right, of observations. So And there's a lot of simple things you can do. Like, for example, if you want to forecast future values in a time series, like there's some very traditional techniques such as ARIMA modeling or ARMA or whatever. There's we try to do a lot of anomaly detection, and for that, you could even do some more other statistical models such as Markov chains, or something like that. But I feel like in that particular context, it's not like you can't do anything without deep learning, but with some you could potentially use RNNs and LSTMs over there, and it would just be like an additional layer of sophistication. I
Mm-hmm.
think that's kind of how I see it in the context of my personal work, is that it's because I get to work with time series data, and because there's already a lot of simple but fairly successful models that can handle time series data.
Mm-hmm.
It's still good to have those as something to depend on, but it's good to explore these kind of new tools as well. And so any sort of industry that deals with time series, I work with utility analytics, but people I guess who work in finance, people probably who work in healthcare, like if they're looking at some time series cardiogram or something like that, and probably people who work in NLP. Again, texts are just like a sequence of words or sentences. So I guess anyone who's working in there, she or he would have to, or might want to use RNNs or LSTMs.
Definitely, definitely. And it looks like we have a few more comments and questions in the chat. So Sharif has said, I agree that one has to understand what the architecture is about, and I think it is similar to knowing how the scikit-learn models work, but the learning curve is steeper for TensorFlow, so that definitely echoes what you said. Yep. And then Abdullah asks, what would you suggest if I want to build an OCR, what specific architecture would they use? What do you think?
I'm not sure if I'm familiar with OCR.
Let's see. Optical character recognition?
I wouldn't know. Sorry.
No, that's okay. Yeah. So that's not a problem. Let's see. And so Sharif also says the latest one is ResNets, I believe, but it will depend on how much time and resources you have for training. The state of the art is moving through. Keep an eye on ImageNet winners. Okay. Yeah, definitely. Cool. Yeah, so that would be OCR, I guess. Okay, great. So I think if that's all the questions we have for today, I think we did cover a lot of the actual chapter, and we got some more discussion going afterwards, which is really great for our viewers. So I think we can call it if you're comfortable, Sahib. Yeah.
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 Sounds good
Okay.
to me.
Wonderful. So thank you everyone for joining us. So this has been another great session on a Saturday. We know that we love to get together and learn on Saturdays, and we're going to continue doing this, of course, every week that we can. We're getting closer towards the end of this book. Well, sort of. So we actually want to start taking suggestions for what to read next. So if there's another specific topic or area of artificial intelligence or deep learning that you're very curious about, or you want to cover, or you think would be very helpful for people to know in order to be, really at the edge of this type of technology, please let us know, write it in the comments, or include it on our meetup page. So again, our meetup is the AI and Deep Learning Enthusiasts. We're located mainly out of San Francisco, but we also obviously host our online sessions. We've also started hosting, we've been hosting workshops in the Bay Area, and now also in Oslo, Norway. So we just got done with our second workshop there this past week, which was really wonderful. And we're going to continue actually hosting these sessions. Our plan is to now go and travel around the world hosting these workshops, as well as we're launching a full program for artificial intelligence and deep learning to kind of teach people through the basics in engineering in Python and going through machine learning, using things like scikit-learn and TensorFlow, and then all the basic concepts for deep learning as well. So it's been a lot of fun kind of putting this together and learning alongside you guys. So thank you again for joining us, and then don't forget, if you want to also be a volunteer presenter on one of these sessions, please just sign up on our on our Excel spreadsheet, which is located in the YouTube description, but then also on the Meetup page. Oh, and then this upcoming weekend, if you're located in the Bay Area, we also have a huge hackathon that's coming up. And that's the AI and Genomics Hackathon, and we've partnered with some really awesome folks at the Artificial Intelligence Silicon Valley nonprofit organization, as well as the NF2 data project. So specifically, we're really grateful. We have one of our organizers has actually donated his data set. He actually got diagnosed with NF2 cancer. It's a type of tumor. It's a very rare type of tumor that does not currently have any type of treatment or cure. And so the goal is to use AI and machine learning to help further research in this area. And he's hoping to build out a foundation actually for his cause. So if, that's the link to that hackathon is actually also posted within our Meetup page. So if you're interested in getting involved, we have still opportunities to volunteer, as well as you can join as a participant online. To join as a participant in person, unfortunately, those spots are already taken. But you can join as a participant online. You can volunteer and kind of also, if you want to do a presentation, if you're familiar with the areas of AI or genomics, or specifically NF2 cancer, we're also still taking presenters or mentors for that as well. Excuse me. But we've also partnered with Google Launchpad, so they've been an awesome sponsor for us. So Google Launchpad, they're also donating computing cloud credits for us for the hackathon, as well as like food and everything for the event, which is really amazing. So I think it's going to be a super great event if you want to get involved. We're trying to do more stuff like this all the time, you know, in this area and then also in other places around the world. But yeah, thank you for joining us. We really appreciate your time, and we really appreciate our presenters' time. So Heath, this has been amazing. And yeah.
Thanks for having me, Laura.
Yeah, of course. And we'll talk to you soon.
Great. Thank you, everyone.
Bye, everyone.
Bye.